So it's been a long week. We're rounding out integration techniques. Section 8.5, partial fraction decomposition. Section 8.6 is kind of a review of 8 through to 8.5. So you got the handout on that already. We'll briefly go over it, but there's nothing new. And then there's some leftover integration stuff we'll talk about next week about using tables and things like that. But pretty much this completes our study of integration techniques. We started off Section 8.1, basically the basic techniques in U substitution. Section 8.2, product rule, integration by parts, reversing the product rule. Section 8.3, powers of trigonometric functions using identities. Section 8.4, integrals involving radicals that can be turned into things in 8.3. Powers of trig functions. And then finally today we're going to talk about partial fraction decomposition, which talks about rewriting rational functions to make them easier to integrate. So before we jump into this, are there any questions on the stuff we've done so far this week? Or you've been able to keep up, work through the examples? So at the end of class today, we'll talk about the take-home, we'll talk about the test. Remember the test 0 and the take-home. Test 0 is due Friday by midnight. That's the federal financial aid attendance requirement. And then the take-home and the test are due Sunday by midnight. And then next week we just start new stuff. All right, so what's the idea behind partial fraction decomposition? Well, once again, as happens often in calculus, we're going to be undoing some algebra. So in algebra class, you would normally start with something like on this side of the equation, and you would get a common denominator. To write it as the single integral, or single term 1 over x squared minus 25. You follow? However, from a calculus standpoint, if I want to integrate this would take a lot more effort than integrating each of these. You follow? And so that's why we're going to be undoing this. And if you keep in the back of your mind, partial fraction decomposition is reversing common denominators. That helps these rules make sense. So once again, we're going to have to appeal to some high-level algebra here about factoring polynomial functions. So we've got some big theorems from college algebra that no one remembers. If you have a polynomial function, it's always possible to factor it down into linear factors. So factors that look like mx plus b's, along with quadratic factors, ax squareds plus bx's plus c's, where the quadratic don't have real number solutions. Those are called irreducible quadratics. So for example, let's look at this rational function here. This is a ridiculous rational function. All right. You look at that denominator. If you look at even x squared, if you see x squared on its own, think of that as an x minus 0 squared. So linear factors, the x is to the first power. So x plus 5 is a linear factor. 2x plus 1 is a linear factor. This is called a repeated linear factor because you have 2x plus 1 times 2x plus 1 times 2x plus 1. So when you hear the word repeated linear factor, it means you've got a linear factor to a power. The x squared is considered a repeated linear factor. It's x minus 0 quantity squared. Okay? These two quadratics are called irreducible quadratics because if you try to set them equal to 0, you're going to get non-real solutions. You remember the quick way to check that? There's that thing called the discriminant. If it's bigger than 0, you get 2 real solutions, distinct. if it's equal to 0, you get 2, but the repeated real solution. And if the discriminant's negative, you get 2 non-real solutions. So irreducible means you can't factor them into linear factors in the real numbers because they have non-real zeros, right? Non-real solutions. So a little algebra review there. Okay, now here's the recipe. So now this is a recipe. So if you're going to break this thing down into these smaller fractions, you have to think, okay, what denominators contribute to that big denominator? All right, so let's look at the x squared. You got an x squared down there. That would have to be part of the least common multiple of the contributing denominators. So you could have a denominator of x or x squared. Both of those would factor into that. You follow? And if you have a linear factor or repeated linear factor, you're going to get away with having just a constant in the numerator. X plus 5 is a linear factor that could contribute to this. So we have a constant because it's linear. 2x plus 1 is present, as well as 2x plus 1 squared and 2x plus 1 cubed. These are all contributing linear factors, so they all have constants up there. X squared plus x plus 1, we could check the discriminant there. The b squared minus 4ac. A, b, and c are all 1. That's an irreducible quadratic, so that's going to be present. And up top we have a generic linear factor then. 4x squared plus 3, likewise irreducible quadratic. That's repeated twice. So we have generic linear functions on top of those. Okay? So it's a recipe. It's a big theorem. It goes back to the structure theorems of polynomials. So here's how we integrate rational functions. First off, we do a quick check to see if we can do long division. Now, on some of the videos, I think in section 8.1, there are a couple examples there where we did long division. So there's some review of long division there for you if you need it. Once you get down to a proper rational function, where the degree on the numerator is less than degree on the denominator, we can apply the partial fraction algorithm. Step 1, factor the denominator. Step 2, write down the form of the decomposition. And then we're going to determine the unknown coefficients. And then finally, we'll integrate each piece. So the integrals that are going to come in really handy for us in this section are integrals that look like this. The integral of 1 over ax plus b dx. All right, what's that work out to be? Well, let's think. What's just 1 over x dx? What's this one? Perfect. This is just a linear substitution for that. So this is going to be more or less this. But what's going to have to be out front to counteract chain rule? Okay? So this will be one for us to remember. Okay? Other ones that are going to come up often is if you have something like this. Like this will come up quite a bit. So that'll come up quite a bit. And last but not least, this will come up quite a bit. What's this one? You remember this one? And the reason why these are going to come up often is because if you look at the form of the substitution, oh, and I guess also power rule also, stuff like this will happen a lot too. Power rules. So if you look at the pieces parts from the decomposition, these are the kind of pieces parts you're going to be coming up with. All right? So it's just best to, that's kind of the integrations you're going to see when you go through all this. So let's talk about how we go through these things. We got our first example here. Got a nice rational function. 4x squared minus 9x plus 3 over x cubed minus 2x squared plus x dx. Now, before you jump in, once again, to these advanced techniques, you want to see if a basic U substitution will do the trick. It's not really helpful. So the next step is we're going to do partial fractions. We need to factor the denominator as much as we can. So we can start factoring that denominator by doing what? What can you pull out of all those terms? Can you factor even further? Whoops. That typo there. Can you factor x squared minus 2x plus 1? Okay, there it is. So step one, try the U sub, and then if not, jump into the partial fractions. Make sure it's a proper fraction, meaning the degree on the top 2 is less than the degree on the bottom 3. Factor the denominator. Are we all good getting that factorization? Now we have to write the form of the decomposition. So this is where we have to think what types of little denominators contribute to this as the least common denominator. So I look at the factors. I have a factor of x. I'm going to need to have that factor represented. I have a factor of x minus 1. And I have a factor of x minus 1 what? Squared. Each of these are considered either linear or repeated linear. So each of these is going to have a constant on top. My next job is to figure out what A, B, and C are. You follow? So how do you do that? There's a sort of a shortcut method called the Heaviside method that I teach you in a video that'll help with some of these. The Heaviside method is to partial fractions what the tabular method is to integration by parts. It works in certain situations, and the situations it works in, it greatly speeds up your workflow. But before I teach you that, just like on Monday, or on Monday, we're going to teach you the formal method first, and then you can speed things up with Heaviside on the video there. So step one is we're going to clear out denominators. So when I multiply through both sides by the x times the x minus 1 squared, on the first term A, the x would cancel, the x minus 1 squared would stay. On the second term, one of the x minus 1s would cancel. The x would stay along with an x minus 1. And on the last term here, the x minus 1 squares would cancel, but what would stay? The x. All right? Now, I want to find values a, b, and c that make this true for all values x. Okay? So sometimes what we can do is we can do a little bit of cheese here. And think about, you know what? Some values of x are going to make this job a lot easier. For example, what if I plugged in x equals 1 to both sides? On the left-hand side, I'd get 4 times 1 squared minus 9 times 1 plus 3. On the right-hand side, what's the advantage of plugging in x equals 1? What's going to happen here? 0. What's going to happen here? 0. What's going to happen here? So x equals 1 zeroes out two of these two of these terms, and I can get what c is right away. What's c going to be? What do you get for C? -2. Is there another x value that I could plug in that would make my life easier? Looking at my original equation, what would be another good x to plug in? 0. If I plug 0 into the left-hand side, zero into the right-hand side, what's going to happen to the b and the c terms if I plug in 0? They're gone. This is going to let me know what a is. What's a work out to be? 3. You follow or not, folks? So if we cheese it, we just pick values that'll zero stuff out. That's going to help us. You follow? Now we're stuck. We still got to find what b is. So how do we do that? Well, to do this, we're going to equate coefficients. Which is how we could actually do this all the time. So let's go left-hand side. I got my 4x squared minus the 9x plus the 3. And on the right-hand side, I've got a times x minus 1 squared, but a I found out was 3. Plus b times x minus 1 plus cx, but I got c was minus 2, so minus 2x. Okay. If this is going to be true for all real numbers, then the coefficients of the powers of x need to match up on both sides. Now I'm after b, right? So if I actually multiplied this out, I would have a bx squared minus a bx. You follow? So that tells me that if I look at the coefficients of x squared, b is going to be involved with that. On the left-hand side, what's the coefficient of x squared? 4. That's going to have to match the coefficient of x squared on the right-hand side. Does that make sense or not? Okay. Do I get any x squareds out of this multiplication? Yeah. 3 of them. So I'd have a 3x squared out of there. Whoops. I'd get bx squared from there. Do I get any x squareds from here? No. So this will tell me that b is what? 1. And now I'm all set. I got my a is 3, My b is 1, and my c is -2. And like everything in this class, you can check this algebraically, or you can check it on Desmos. How would you check this algebraically? Well, you go back to your partial fraction decomposition. A is 3, so you'd have 3 over x plus 1 over x minus 1 minus 2 over x minus 1 squared. Does that in fact equal, went too far back. This 4x squared minus 9x plus 3 over x cubed minus 2x squared plus x. So you could get your common denominator there. That would be reversing your partial fractions. Or you could graph on Desmos the left-hand side, graph on Desmos the right-hand side, and see if the two graphs do what? Match up. You follow? So either way you want to do it. So after all that algebra, now we can sweep in and finish this up with calculus. Because instead of trying to integrate this thing, I can integrate 3 over x plus 1 over x minus 1 minus 2 over x minus 1 squared dx. And these individual integrals should be doable. They should be like Calc 1 doable, right? Because they're just these little rational functions. What's the first one work out to be? That's 3 what? Yep, natural log x, good. What's this going to work out to be?
Natural log of x minus 2.
Perfect. Now how about this one? That's one of these power rules. So you'd add 1 to the power, get -1 divided by that power. There it is. Okay. So once again, partial fraction decomposition is a technique. Just like integration by parts is a technique. Integration by parts comes from product rule. We rewrite the product rule to get a new technique of integration. The stuff we did on Tuesday, the trigonometric integrals, we went back to trigonometry and looked at those Pythagorean identities again. Wednesday, we had some algebra things we couldn't figure out. We went back to the Pythagorean theorem, used identities. Here we're using algebra. Yeah?
Why did the 2 over x minus 1 become positive?
So this is minus 2 x minus 1 to the minus 2 power. So when you add 1 to that power, you get a -1, and then you divide by the -1 in terms of positive.
Okay.
Yep.
Gotcha.
But hopefully you've seen the theme this week of we're just taking stuff we already know and just applying it or reversing it, complicating things to make them easier in the end. Okay. Let's look at our next one here. Here we got the variable t now, so hopefully that doesn't throw you. 4t squared plus 12 over 12 over t to the fourth plus 4t squared. dt. So first we check to see that it's a proper rational function, meaning I look at the degree of the numerator, it's 2. That's less than the degree of the denominator, that's 4. So there's no long division we can do. Maybe we try to factor, maybe we try to do a u substitution. None of that stuff seems to work. The denominator I can easily factor, so let's try partial fractions. What can I factor out of the denominator to get started? A t squared, and what's left? T squared plus 4. Can you factor t squared plus 4? If you set t squared plus 4 equal to 0, you going to get any real numbers out of that? No. So this right here is what we call an irreducible quadratic. All right? So here we go. We have to think of all the denominators that could contribute to this big denominator. This big denominator has a factor of t in it, has a factor of t squared in it, it has a factor of t squared plus 4, linear factor, repeated linear factor, whoops, and this is an irreducible quadratic. So this would be a ct plus d. So I'm trying to find constants a, b, and c, and d, so that this will work for all real numbers. Let's go ahead and clear out the denominators and see what we're working with here. When you multiply this denominator by the a piece, one of the t's will drop out, but one of the t's will be left. When you multiply the denominator by the b part, what's going to cancel out? T squared, but I'll be left with the what? Good. And when I multiply this last term by the denominator, what's going to cancel out? And then t squared is left. Okay. All right, can we cheese out any of these coefficients? Is there a value of t I can plug in that's going to make my life easier? Yeah, 0. 0 looks good. If I plug 0 into the left-hand side, I've got 4 times 0 squared plus 12. And that's going to equal what? The a term has a 0 factor, so that's going to be 0. The b term doesn't. This is going to be b times 0 squared plus 4. And this whole thing will be multiplied by 0. You follow? So this is going to give us what b is. So what's b? Three. And for the other ones, we're just going to have to go through and match up the coefficients. Now, since there's so many coefficients left to find, let's just go ahead and multiply out the right-hand side and gather all the things together that go together. So the first term here, distribute, I'd have an AT cubed plus 4AT plus 3T squared plus 12 plus CT cubed plus DT squared. And now we're going to equate coefficients. So you look at that expression there, and what's the highest power of t that you see up there? T cubed. So let's look at t cubes. On the left-hand side, how many t cubes are there? There's none. So that's going to have to be the number of t cubes on the right-hand side. So going through the right-hand side, how many t cubes do I see? Here I've got how many? A of them. And then here I have how many? C of them. You follow or not? T squareds. How many t squareds on the left-hand side? 4. On the right-hand side, how many t squareds are there? 3 plus D. Let's look for t's. Left-hand side, how many t's are there? None. Right-hand side, how many t's? 4a. And finally, let's look at constants. Left-hand side, what's the constant? Right-hand side, what's the constant? So that didn't really give us that. It's just a nice little check. Now, if we hadn't cheesed out to figure out what the b is, that would have helped us find what b is. You with me or not? So, okay. So here we go. Here's our equations. All right, well, this is nice. I equated the coefficients of t. There's no t's over here. That's the only t there. That tells me that a is what? 0. This tells me d is what? And this, well, if I know a is 0, then this tells me that c is what? 0. Okay? So what's going to happen in general is you're going to get a system of linear equations, right? Which you can solve using like substitution, elimination, or whatever. If you've had linear algebra, you can go all fancy with it, use Cramer's rule or matrices or something. But there you go. So what's this all mean? Instead of trying to integrate 4t squared plus 12 over t to the 4th plus 4t squared dt, we can instead integrate what? Well, a over t, but a was what? 0, plus b over t squared plus ct over d over t squared plus 4, but what was c? And what was d?
1.
You follow or not, folks? And now I can integrate this. That's your power rule. How's the first term integrate? What's that integrate out to be? Yeah. So, yeah. Negative 3t to the minus 1, so negative 3 over t. And what about this next one? What's that? Nope.
Am I not?
This is an inverse tangent formula.
Oh, okay.
That's one of these dudes. That'd be a half inverse tangent t over 2 plus c. Okay. So partial fraction decomposition, you have a rational function that the algebra students have spent hours and hours putting together as a single fraction, and then you come along and say, you know what? I need it. I need it the other way. Make it easier to integrate. All right, so this last one together, and then there's more to do then on the video. Two x squared plus 8x plus 13 over x squared plus 4x plus 7. Now, in order to apply the partial fraction decomposition stuff, you need to make sure that you have a proper rational function. Proper rational function means the degree of the numerator is less than the degree of the denominator. In this particular case, what's the degree of the numerator? What's the highest power of x in the numerator? What's the degree of the denominator? It's also 2. That means we have to do long division. Okay? Degree of the numerator, degree of the denominator. So we got to do it long division first. So here we go. So the first thing, we need to take 2x squared divided by x squared, and that's what? 2. So that's going to go over the constant there, and now I need to multiply and subtract. So I multiply two x squared plus 8x plus 14 and subtract 2x squared minus 2x squared is 0. 8x minus x is 0. 13 minus 14 is what? Negative 1s. That's my remainder. Negative 1s. Now I got to put this together. Bless you. Okay. Instead of integrating this, I'm going to integrate, it goes in twice, so that's 2 plus the remainder, which is a minus 1, so minus 1 over the divisor. Now the 2 we can integrate, that's going to give us what? So now I just got to figure out how to integrate this second piece. Okay. We just did the long division. Okay. So we ended up getting 2 with the remainder minus 1. So there's our 2. And then there's our minus 1. So we're up to here now. So now we're trying to integrate that quadratic. So we'll do that over here. If we think about trying substitution on, or partial fractions on this, we would have to go in there and see if it's an irreducible quadratic or not. So we'd have to check our discriminant here. So our b squared would be 16 minus 4 times a times c. Our discriminant is going to be what? Right. So that means that x squared minus 4x plus 7 is irreducible. Which means we can't break it down any further. You follow? So partial fractions isn't going to help us. All right. So if it's irreducible, what do we do? Right, so partial fractions will be no help. So we need some other algebraic thing to do. So what's another algebraic technique we can use? I think we saw it yesterday. We did it yesterday. We did it. There's a couple examples in 8.1. If you're stuck with a quadratic, you can always do what with it? This one doesn't factor, so we have to do what? What's the other thing we can do with quadratics? Complete the square. So we complete the square. All right, so here we go. Complete the square. The nice thing about complete the square is there's a recipe for it. So remember, completing the square, the recipe is, if your coefficient here is a 1, it's x plus b over 2 squared minus, well, yeah, I mean, it is b squared over 4, but it's easier to think of it as b over 2 squared. So in our particular scenario, it's x squared minus 4x plus 7. Whoops. Oh no. There we go. So there's that x squared plus bx part. The coefficient of x squared is 1, so that's good. Yesterday we had to factor stuff out. We don't need to do that today. X, the b here is negative 4, so what's b over 2? Negative 2 minus b over 2 squared plus 7. So this gives us an x minus 2 squared plus 3. Now once again, the way you would check that this is correct is you would start here, FOIL this out, and then add 3. You'd get your x squared minus 2x, there's your minus 4x, plus your 4, plus your 3 gets you back to what? 7. It all works out. Beautiful. And once again, this is one of your arctangent formulas, but instead of an x, you've got an x minus 2, but that's a linear substitution, so we're cool with that. 3 is the square root of 3 squared. So that is that part of the integral. But as I mentioned on Monday, a lot of this chapter is about keeping track of what you're doing. This was just one part of the integral that we started with. You follow? So I got to put that back in. My final answer is 2x minus that integral. So let's put this all together now at the end. The integral of 2x squared plus 8x plus 13 divided by 2x squared, x squared plus 4x plus 7 dx equals 2x, from the division there, minus this arctangent. There it is. You check your answer taking the derivative, reversing the algebra. You can check your answer on Desmos. But there it is. That's partial fractions. And that, oh wait, I somehow switched this. Look at that. This answer is correct because for some reason I switched this plus to a minus. It's fine. Okay. Video here. So this is where I introduced the Heaviside method. Which the Heaviside method is just a shortcut. You know how we would cheese values? So let's go back to some values we cheesed here. So this is what the Heaviside method is. You see how we plugged in the x equals 1, and that gave us what the c was? So if you look here and look at this, if I set this equal to 0, x is equal to 1. You follow? When you multiply through by the common denominator, this x minus 1 factor is going to get attached to each of these things. You follow? So what's going to end up happening is if I go back over here and I cover this up and plug 1 into what's left over, look what I get. Minus 2 over 1, which is minus 2. So it's the Heaviside method. Heaviside was an electrical engineer who had all these shortcuts. The mathematical community shunned him for it. And then after he died, the mathematical community went in and said, oh yeah, this is all good stuff. This is mathematicians, right? Just like your grandpa. You know how they are. For example, here, x is 0. If I cover up the x and plug 0 into what's left, I get a 3 over 1. So that's the Heaviside method. So we talk more about that here, and we use it. When it works great. Now, it's not going to be a cure-all. It's just like integration by parts doing the tabular method. It only works for certain things, but when it works, boy, is it great. The Heaviside method works for some of these, not all of these. 3 more examples of parts. And then these integrals are a little dicier. They're more creative in that you have to make a substitution, but then you have to like mess around with the substitution to turn it into something like integration by partial fractions or something. Okay. And then there's book homework. All right, now section 8.6 just goes through 8.2, well, I guess 8.1 because that's the review stuff, up through 8.5. So here's this. Now, on your test, which I have here, I thought I had there. The last page of your test is all these basic formulas. All right, because I don't want you, like if you're still reviewing, because this class is 8 weeks, right? If you're still reviewing Calc 1, you haven't had time to even. So you're going to have these basic formulas on the test. So like today when no one knew, I don't know what that is, you'll know. Okay, it's on there. You still need to be well versed in what's going on to know what strategy to use. Here's your basic integration properties. And then the basic strategies. Okay, so this is the stuff like we reviewed from 8.1. And then we get into the parts, trig powers. You follow? And then these are just more examples. Now what I did is I don't work these out. There's not a video with these solutions. I would encourage you to work through these, but the big thing I think, the value for this for you, and this is the homework from the book then, is to just think, okay, what strategy would I use? You follow? And then that's what's on the back is the different strategies. You with me or not? So that's, But once again, think of this as 12 more examples to work through if you want. You can check them on Desmos if you need to. You follow?